Hello, my name is Cholhung Park, the graduate student of Sogang University in Korea. Today, I present about a comparative performance analysis of vulnerability detection schemes for specific blockchain application. Here is the outline for the presentation. First is introduction. Second is smart contract vulnerability about anonymous electronic voting and peer-to-peer energy trading system and other common vulnerability. And then I present about vulnerability detection schemes for smart contract and comparison of detection schemes for specific application and then result. First is introduction. There is a lot of blockchain smart contract security vulnerability case. The DAO and Perti multi-sig wallet cases are well-known case about security. There are many incidents caused by security vulnerability in smart contract. There are a lot of vulnerability detections existing, but they have a lot of limit. First, they try to create a detector for every situation, so there are not many vulnerabilities that can be detected, and a lot of detectors, including jails, operate at low level, so that makes the program heavy and difficult to tell where the problem occurs. So we will study about detection scheme for specific application. Second is smart contract vulnerability. Smart contract vulnerability pose a significant threat because they can lead to financial loss, breaches of privacy, and disruption in the normal operation for a network. Smart contracts are executed on blockchain network which are decentralized and immutable, meaning that once a smart contract is deployed, it cannot be changed or updated without the agreement of the network participant. This makes the detection and correction of vulnerability more challenging and can leave network vulnerable to exploitation. In addition, vulnerability in smart contract can impact the integrity of the entire network, potentially exposing user data and asset to malicious actor. Given the increasing use of smart contract in various applications, including financial, insurance, and supply chain management, it is crucial to identify and address these vulnerabilities to ensure the safe and effective use in this technology. However, the smart contract vulnerability can vary depending on the specific application. For instance, in a voting contract that requires a deposit to participate, it is crucial not to allow multiple payments to be sent to the same individual. So this paper will examine these cases more closely through anonymous electronic voting and peer-to-peer energy trading system smart contract. This is anonymous electronic voting's vulnerability. First is the time manipulation vulnerability. The remain function checks whether the current block's timestamp for within specific time range. However, this approach is susceptible to time manipulation attacked by miners who can include blocks within manipulated timestamps to circumvent time-based restriction. Second is access control vulnerability. The owner variable is used to restrict access to certain function, but the enroll candidate function allows anyone to enroll a candidate if it is called before the reg candidate time has passed. This means that anyone can be manipulate the election by enrolling multiple candidates. Second is integer overflow underflow vulnerability. The enroll candidate function increase the k variable each time a candidate is enrolled. If k reach its maximum value of 2 to the power of 255, it will overflow and wrap around to zero, potentially cause unexpected behavior. In addition, the bots variable for each candidate is unsigned integer, so it is susceptible to underflow attack if someone tries to case negative bot. Third is very famous vulnerability in Trinity. The bot function send either to the caller, which can trigger reentrant call to other contract. If the recipient contract is malicious and reentrant, it cause read to expect unexpected result, including the thief of user funds. And next is denial of service vulnerability. The telling function calculate the tally for each candidate by iterating through all the voter and their votes. If the number of voters is very large, it could cause the function to consume a lot amount of gas and become unresponsive, potentially leading to a denial of service attack. Next, there are peer-to-peer energy trading systems, smart contract vulnerability. As with voting, there is some famous vulnerability about, for example, integer overflow, underflow vulnerability, or reentrancy vulnerability. And there are some others vulnerability I present about that. First is external contract core with arbitrary input vulnerability. This is in the buy energy function. The market contract is called with market that core value is MSG dot value. This is potentially dangerous because arbitrary input can be sent to market through the empty data field. Next is unchecked array access vulnerability. In the buy energy function, offer buyers writer to the offer ID that buyers array without checking if the array has enough capacity to hold the new value. This could lead to an out of bounds writer write if the array is already full. And next is unprotected either withdrawer vulnerability. The withdraw function allows anyone to withdraw the balance of the contract. This could be a vulnerability if the contract's balance is not probably secured and the actor can take control of it. And there's some other vulnerability like core stack overflow vulnerability, transaction origin use vulnerability, and block dependency vulnerability or transaction order vulnerability. Uh, Next is vulnerability detection schemes for smart contracts. There are some detection scheme, a detection tool for smart contract. The famous one is JAWS, and then Basin VAs, Misril, Mayan, SmartCheck, and Smartian. The first, JAWS, is the most popular vulnerability detection scheme. JAWS is a static analysis tool that aims to verify the correctness and fairness of smart contract. The tool employs a combination of abstract interf- interpret- interpretation, symbolic model checking, and constraint statement to perform a rapid security analysis of smart contract. JAWS is capable of detecting six security vulnerabilities, including reentrancy and integer overflow, underflow, and transaction order dependence. Second is version VS. Uh, this is a platform for smart contract security detection that utilizes formal verification method. This tool is capable of automatically identifying 10 major and 32 minor security vulnerabilities in smart contract and provide a precise location of the vulnerable code along with modifications suggestion. Third is Misril. Misril is a static analysis tool for Ethereum smart contracts that combine concept analysis, taint analysis, and control flow verification. It aims to detect common vulnerability in smart contract, including reentrancy, overflows, and issues related to exception handling. First is Mayan. Mayan aims to identify three types of problematic smart contract. Greedy smart contract that frees a large amount of computable resources, prodigal contracts that waste gas by uh, sending transactions needlessly, and suicidal contract that can be exploited to destroy their own code. And then Smart Check. Smart Check is an intensive static analysis tool for smart contract, which convert the source code into an XML-based intermediate representation. Then Smart Check detects the smart contract vulnerabilities in the middle of representation of the contract based on the analysis of XPath pattern. Moreover, this tool can be improved in multiple directions, such as improving the grammar, makes patterns more precise, and adding new pattern. At last, Smartian. Smartian presents a new approach to improve smart contract forging, a technique used to identify security vulnerability in smart contract. They propose combining static analysis with dynamic data flow analysis to improve smart contract forging. And smart static analysis is used to extract information about the data flow of the contract, while dynamic analysis is used to observe the actual execution of the smart smart contract. They claim that their approach can perform more effective and efficient forging by guiding forging to focus on the most important part of the contract and avoid areas that are less likely to cause security issue. Uh, and I present about comparison of their schemes, six schemes for specific application. This is a table of installing and running each smart contract vulnerability detectors. Uh, First, despite the popularity of smart contract as a detector, its source code is not publicly available. Several study has compared the performance of jails, but the source code is currently not publicly available and can not be verified through installation execution. Similarly, Persin BS operates as a service platform, but its source code is not publicly available, so it is not possible to verify it by installing and running it directly. Next is Mislead can be installed through consensus GitHub, and its execution results are similar to those of several studies. It detective all of our expected vulnerability except V2 and V8 uh, and V13. Mayan is currently not available for normal installation. Mayan's GitHub has instruction on how to install it. However, uh, Mayan did not detect any vulnerabilities except V4 and V7. Uh, it means that something probably went incorrect during the installation process. Smart Check can be installed using their installation method through GitHub. By looking Smart Check's GitHub, we can see description of over 50 detection rules. However, it didn't detect any vulnerabilities except V1. It is possible that this because SmartCheck has released on GitHub for than 4 years. Finally, SmartTN is an F Sharp based project, or you can check their GitHub for installation instruction. Interestingly, SmartTN detect the same reentrancy vulnerability, but not V4 and V7. It seems that the fuzzing process did not cause the V4 reentrancy issue. And last is result. In this paper, we review the vulnerability that can exist in smart contracts and the detectors that detect them. Based on their performance in different study and the result of their implementation in real case, we want to create an application-specific vulnerability detector for smart contract. Each smart contract can have vulnerability of different risk. On the other hand, there may be cases that not actually a problem that can be judged as vulnerability. Through this paper, we were able to see different vulnerability detection results for the same code in practice. In the future, our goal is to study application-specific smart contract vulnerability detectors by finding the code vulnerabilities of smart contract in each application and applying them to smart contract in similar application. Uh, Thank you for listening.